All right, so what I'm going to be looking at here is I'm going to be looking at sets, and we're going to talk about some review for sets. And this is our second exam. And so first I'm going to talk about what a subset is and the general idea of sets and subsets. So let's take a look at, let's say for example, we want to determine whether the first is a subset of the second. So we have a question like this. So the set of people who speak English and the set of people who speak English with an Australian accent. Okay? So is the first a subset of the second? So if we think about this, let's say for example, our set, our primary set, if we read this correctly, is the set of people who speak English with an Australian accent. Okay? Okay? So that's all the people that we want for our primary set. Okay? And then our subset, in order for the set of people who speak English to be a subset, if X is a person who speaks English, then X is a person who speaks English with an Australian accent. And what that is that would be if A is our English set and B is English with an Aussie accent, then A would have to be contained within B. Okay? So if X belongs to A, then X also belongs to B. Okay? Well, what if somebody, say for example, is like me, and I speak English, but I do not have an Australian accent, unless Australian accents don't sound like what I sound like, and that's just not true. So consequently, I belong to A, okay? X belongs to A, that is Dr. Sweeney, but not B. Okay, so basically what we have here is we have an instance that looks somewhat like this. Okay, so there's a group here. These are those who speak English and speak it with an Australian accent, and actually it's more even like this, right? So here's all the people who speak English and speak English with an Australian accent, and then say for example, here's me, George, okay? And I am not within this group of the people who speak with an Australian accent. So A is not a subset of B. Or the set who speak English with an Australian speak English is not a subset of the people who speak English with an Australian accent. All right. So that's the first one. Let's take a look at the second one. B, the set of students studying discrete mathematics, the set of students studying data structures. Okay? So let's say, for example, we look at this one now. So we're going to let A equal the set of students in discrete structures. Our class. B is going to be the set of students studying data structures. Now, so we want to know, is the first a subset of the second? So is A a subset of B? Okay, so if X belongs to A, does X necessarily also belong to B? Well, let's imagine that we have a student, all right, and who is taking discrete structures, all right, but is not taking data structures, or vice versa, one who is who is taking exactly discrete structures but not taking data structures. There's probably several people inside of this class that are doing exactly that. There are probably students who are doing both, okay? But it's not necessarily the case that if a student is taking discrete structures that they have to be also studying data structures, okay? So what that means is that this is A, right, intersect B, yes? So there's probably students in there. But there's also probably students who are over here, over here in A, right, who are not here in B. Okay? Those are our X's. And since that's the case, A is not a subset of B. Okay? So we get the false. Let's actually talk a little bit about what it would require for us to have A be a subset of B. Okay? For A to be a subset of B. All right? What we have to have is if this is B, then A has to be contained totally within B. Now, so this is the kind of Venn diagram. That's the Venn diagram that would look like that subset relationship. Another one would actually look, and it's a little weird, but it in fact would be where A equals B, where the two are the same. So this is A and B, right? They're the same set. So you can have one or the other. This one here, this is called your proper subset. All right? And this is called equality. Put the two of them together and you get this idea of the subset. And so that's what we mean when we talk about a subset. The next idea here that we want to work with is this idea of Duples or Cartesian products. And so this is again a set idea. It's just one set idea, but it's one that might be a little bit tricky. So I wanted to go over it. And let's say, for example, I have A cross B cross C. Okay? And what this means is that I'm going to have what we call triples. Okay? So these are things that are called triples. And the first element of the triple is going to be an element of A. The second element of the triple will be an element of B. And the third element of the triple will be an element of C. So we end up with A, X, 0. That's one element. Okay? That's one of the elements of A cross B cross C. Then we'll also have A, Y, 0. Then we'll have A, X, 1. And we'll have A, Y, 1. So those are all the A values in A cross B cross C. Okay? Then I'll go on next to my B values. B, X, 0. B, Y, 0. B, X, 1. B, Y, 1. And those are my B values. And then I'll have C, X, 0. C, X, C, Y, 0. C, X, 1. C, Y, 1. And I just chose to do it that way. You don't have to do it exactly that way. But this way, at least, it kind of helps me to keep straight what all the elements are inside of my Cartesian product. Okay? And notice these are triples. And the total number, the cardinality of A cross B cross C, and don't forget that this is what those lines mean, is going to equal, you got the 3 elements in A times the 2 elements in B times the 2 elements in C, so that equals 12. So if I go in and I count, there should be 12 elements there. That actually is a really good way for me to go and check my work. Now, the thing is that these are all ordered tuples, and the order does actually matter quite a lot. This is especially the case if, say, for example, you're working standard math, right, where, you know, one's the X component, one's the Y component, one's the Z component. So if we have C cross A cross B, we're going to end up getting a different set of results. We'll have the same number of results. We should still have 12, and we'll look at that in a second, but they're going to be in a different order. So we'll start with zeros. We'll start with the 0, 0, and then A comes next. 0, A, X, and then we'll do 0, A, Y, 0, B, X, 0, B, Y. Back up. Then I'll have 0, CX, 0, CY. And now I'll move on to my ones. 1, AX, 1, AY, 0, 0, BX, 0, BY, 0, CX, 0, CY. And there's our relationship. Notice we can go through, we can count them. There are 12 of them, which is exactly what we expect, right? Because the cardinality of C cross A cross B should end up equaling 12. And there we go. And that's how we utilize Cartesian products. So things like this, you know, we have, you know, A, B, C, X, Y, 0, 1. What we want to get about Cartesian products is that these values could be anything. And when we're working with computers, oftentimes we want to get that, like literally these values could be whatever we want. Okay. So now let's jump into something a little bit more difficult. We're going to now work with our set operations, unions, intersections. We'll use some differences here. You're also expected to know things like complements, complements of complements, things of that nature. And so what we're going to do is we've got some sets here, and we're going to actually generate new sets from these set operations. I'm going to draw some Venn diagrams in order to help illustrate here. But all we're really asking for here is to just find what the set actually would end up being. So let's take, for example, we got A, right? And we have B, and we have C. Okay? Here's A, B, and C, and we're going to look at A here. Okay, A, B, and C. And so we want A intersected with B union C. So B union C, we're going to mark that. B union C is this yellow part here, okay, in the Venn diagram. And what we want to know is when we intersect that with A, right? So we do B union C first because it's in the parentheses, and then we're going to intersect it with A. So when we intersect it with A, that's that region right in there, okay? So it's all the stuff that is in B and A and also in C and A, okay? Now, what I'm going to do is I'm going to generate my my set, and I'm going to use the order of operations here. So first I'm going to find B union C. So B union C is going to end up equaling 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Because B union C means everything that's in B or C. And if you take a look here, you actually could see those are all the values that actually are in B and C. Now what I'm going to do now is I'm going to intersect that. So A intersected with B union C. Okay? And we're just going to look here and we're going to say, okay, what are all the values that are in both? So if I look here, I'm going to say, all right, so 0 is in both. Okay, I got 0 in A and 0 is in B, union C. 2 is in both, so 0, 2. 4 appears to be in both as well. 6, yep, 6 is in both. It looks like 8 is also in both, and 10 is in both. Okay? So it turns out, that actually ends up being A. That just happens to be how this works. And that is because A is actually a subset of B union C. Okay? Not B by itself, not C by itself, but actually B union C. All right? So what I did there was first I union B union C, and then I took the intersection with A secondly. All right? I utilized the order of operations. All right, what about A union B union C? Okay, well, in this case, we can actually do this in any order that we want because of associativity. So we've got B union C, so let's do A union B union C. Okay, now, what that looks like, if we draw a Venn diagram, is, let's say, for example, we have something that looks like this. Okay, the Venn diagram then is going to look like this. It's everything, including the intersections. All right? So anything that's in A or B or C or any combination of the three of them, because we're not actually using the exclusive OR. So I go in and I'm saying, okay, so I got A, union B, union C. Well, let's see. Let's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We know that A actually is a subset of B union C already because we saw that before. So nothing actually gets added there. You can go in and check, but A union B union C is simply equal to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And in fact, if we kind of think about this, this is in fact this. Here's B union C, and A is kind of like within B union C because it is a subset of B and C. So here's A. A is in both, and there is in fact sets that are within all three. All right, now we got a somewhat more complicated one. Let's look at A minus B union A minus C. So let's pick up another sheet here. So let's actually generate, we've got our Venn diagram, okay, that we've seen before. Now, this one's a little bit harder to do the Venn diagram with, so I think we're just going to not do it for right now. Let's just talk about what it does look like if you're going to do B minus C. All right, so here's B, here's C, and B minus C then is just going to be all the parts of B that are not also parts of C. So it's going to be just this area here. It's that exclusion. Okay? It's that area. So now, what I'm going to do is I'm going to go in here and I'm going to generate, I'll generate first A minus B. Okay, so I've got A minus B, and that's going to end up equaling, okay, notice that the things that are in A that are also in B, so we've got 2 is one of the elements, so I've got 0, well, 0 is in B, so that can't be it. 2 also in B, 4 is in B, and 6 is in B, so A minus B is just going to be 8 and 10. So we got 8 and 10. Those are the only elements that are going to be in A minus B. Okay? If we go now to A minus C, now what I'm going to do is I'm going to look at A, and I'm going to compare against what I've got in C. Well, now if you look at C, C's got 6, C's got 8, and C's got 10. Those are the ones in A. Oh, and C's also got 4. So that means A minus C is just going to be 0, 2. It's just going to be the first two values. Now let's go with B minus C. So B minus C now is going to equal, okay, we got B, and we want to see what are the values in B that are not also in C. Well, C's got 4, 5, and 6. Okay, so that means that B minus C is just going to be 0, 1, 2, and 3. So now, if I union the 3 of them together, I'm going to take the union of all of them. That's going to be all the values that are in all of them. So this is A minus B, union A minus C, union B minus C. That's going to end up equaling the set. We'll start with 0, 0, 1, 2, 3, 8, and 10. And that is A minus B union A minus C union B minus C. So when we're actually going through and doing set operations, this is what I recommend you do. You start out with anything that's inside of the parentheses and you figure out what those sets are. And then you use the outside parentheses values in order to, put them together. Either utilizing intersections, utilizing unions, whatever it is that you think that makes sense for you. Okay? Well, whatever is actually written there, not what makes sense for you, what's actually written there. And then that way, it's very systematic. You can actually get the values that should be inside of your sets. So what we're going to do now is we're actually going to draw some Venn diagrams in order to show some sets of sets. Now, the idea here is not so much that you need to be able to draw Venn diagrams, although that's a very handy skill to have, but that sometimes we want to be able to visualize sets and operations on sets, right? And Venn diagrams can actually be really handy to do that. So let's say, for example, I have A, and what I have is I have A, and that's intersected with B minus C. Okay, so here's A, here's B, and here's C. So the first value, that's actually within our parentheses. We've got to do that first. So I'm going to utilize, okay, I'm going to use, say, for example, the yellow in order to do that. Now, B minus C is going to be all the values that are in B, but are not in C. So there's B minus C. Okay? Now what I want to do is I want to intersect that with A. Okay, so this is anything that's in that yellow circle. All right? We're going to intersect with A. So anything that's in both of those circles. That's what it means to intersect. So what that is that that's just this section right in there. So that, in fact, is going to end up being A intersect B minus C. Okay? Next up, let's look at A intersect B union C, C union D. Okay, now we've got 4. Let's use a 4-shot Venn diagram. Can sometimes be a little tricky to do, but can be done. Okay, There we go. Yes. Should be all right. Looks a little strange, I know, but that's okay. So here's A, here's B, here's C, and here's D. And we want to know A intersect B, union C, union D. So we'll start out, we'll do each one of those ones that are in the parentheses directly. So we'll start out with A intersect B. So this is A intersect B. All in that yellow area is A intersect B. Okay? Parts of it are in D, parts of it are in C, right? But we do know that it's going to be in A and it's going to be in B. And that's C union D. So now we've got C union D. Okay? So now that's C union D. It's in the blue. And now, so we got A intersect B union C union D. So we'll utilize maybe a pink. And this gives me this section right here. And there we go. And that is everything that is in all three of those. Okay? Let's take a look at one more. A minus B intersect C intersect D. Okay? Again, we're going to do one of these four toppers. So let's start with the values that are in the parentheses. So B intersect C intersect D. So here we go. Here's B intersect C intersect D. So B intersect C intersect D. We've got it's this section right in here. That's B intersect C intersect D. And then, so now we're going to take A minus that value. So A minus that value is going to be everything that's in A but is not those values. Okay? So that's going to be, that is the A minus is going to be in the peak. And there we go. And that's a Venn diagram of what that looks like. All right? So A minus B intersect C intersect D is anything that's in A but that is not also in B, C, and D. Okay? One of the things that I should say that you're going to want to be able to do with something like this is, let's say, for example, you're asked, here's a set or a set of sets. Describe whether or not somebody's within a particular set, or an individual or a member of the set is in the set. Okay? Is it there? And then describe how you know. Okay? Or whatever. That is one of the kinds of questions that you might actually be asked in order to kind of work with sets and show that you understand how set operations work. Okay? So being able to draw a Venn diagram might actually become helpful for you to be able to do activities like that. All right, so now let's take a look at something that we've talked about quite a bit inside of class, but that's utilizing set identities to prove equivalencies. So let's say, for example, I have A union B intersect C all in complement is equal to C complement union B complement intersect A complement. And one of the things that I want to do here is I want to get out my set of identities, right? Because you're going to be able to utilize those on the exam. It's open book, so you want to make sure that you have access to those identities. So we'll start out here, and what I want to notice is that this has got a complement, and if I've got a complement, then I'm going to utilize De Morgan's law. Okay, so I'll start out with A union B intersect C all in complement is going to equal A complement, okay, and then that'll be intersected with the complement of B intersect C. And that's De Morgan's law. Then, 2, I'm going to get the equivalency here. This is now going to be A complement intersect, and then I'll use De Morgan's law again, B complement union C complement, right? And that's again is a De Morgan's law. And we don't actually have to put numbers on here because what we're doing is we've got equivalencies, right? It's always the previous value or the previous identity that the previous statement that we are going to be making equivalent to. So now what I want to do is I want to notice, oh, okay, well, this is in a different order. Like the signs are all the same, but they're in a different order. So what I'm going to do is I'm going to switch out. I'm going to make this B intersect or B union C complement intersect A complement, and that's by commutativity. And then 4, we're going to get C complement union B complement intersect A complement, and that also is by commutativity. And thus we are finished. Okay? So the whole idea here, you don't actually have to put any of the numbers in here when we're actually doing these kind of proofs by set identity. What you want to do is you would just want to like basically, you'll write down the immediate, whatever thing that you are in fact saying is equivalent to your previous statement, and then you just put the reason right next to it. And that's your proof. All right. So there are a lot of these inside of the homework. I'll make the solutions available to you so that you can look at them. But definitely, you want to make sure that you're practicing those as well. Okay, so now let's suppose that I want to show that A union B is a subset of A union B union C. And so there's a basic structure for showing that that this statement is true. And what we're going to do is we're going to suppose, so what we want to look at is we want to show, okay, one set is a subset of another. So what we're going to start out with is we're going to let X belong to A union B, the group, right, that is on the left-hand side of the proper subset, or the subset statement. So X belongs to A union B. So X belongs to A, or X belongs to B, right? Okay. X belongs to A or X belongs to B. We could use set notation if we wanted to. We could say, for example, X belongs to A or X belongs to B. And we'd write it in set notation if we wanted to do that. Okay? Or you could just write it like that. I'm perfectly fine with that. So X belongs to one or the other. And what we're going to do is we're going to use cases. Right? Suppose X belongs to A. Then X belongs to A union B union C. Okay? By definition of a union. All right? So basically we're saying, okay, so X belongs to that, then X is going to belong to my set, all right? And by, in this case, the definition of a union. And then, well, what if suppose that X belongs to B? Then X belongs to A union B union C, right? By definition of a union again. All right, so X belongs to A union B union C. Thus, A union B is a subset of A union B union C. And we're done. Okay, so the idea of how we prove these things where we want to say, okay, one set is a subset of the other, is we basically say, okay, well, we'll start out with X belonging to the smaller set, right? And then we show that means that X must belong to the bigger set, okay? Or basically the idea of X belongs to the left-hand set, then X must belong to the right-hand set as well, okay? X is in here, then X must also be in here, right? Now, this concludes the work that I've given for the sets in terms of the review. So you can kind of look at these things. Now, this doesn't mean necessarily that the problems are going to look exactly like this. This is just to have you kind of think through the big ideas that are going to be in the set portion or in the entirety of this particular test. So you want to be able to do these things, but then you want to basically be able to work through anything that's inside of the homework, because a lot of the stuff in the set stuff is big idea stuff. All right? Make sure that you understand the definitions. Make sure that you kind of understand how the identities and how they're equivalent to each other. Definitely make sure that you understand De Morgan's laws, all those kind of things, because all that stuff is going to become really crucial. All right? Okay, so make sure that you go into this review section, the review set. You read through it, you know all the topics that I put into there, and you feel really comfortable working through these problem sets.